All right. Hello, everyone, and thank you for joining today's ECSS Symposium. Your microphones are muted by default, but there will be time at the end of the presentation to ask questions. Also, feel free to pose questions in the chat box. Without further delay, I would like to introduce Rob Quick, who will be presenting the digital object architecture and enhanced robust persistent identification of data. Thank you, Rob, for presenting. The floor is now yours.
Thank you. Can you hear me okay?
Yep, I can hear you just fine.
Okay. I'm actually going to escape out of here and start this again so I can watch the time in the presenter view. Good afternoon or good morning, everybody, depending on where you're located. Thanks for taking your time to spend what'll be about 45 minutes with me talking about the digital object architecture and a NSF project we have called Rapide, which is the robust persistent identification of data, and its newer version, which is E-RPID, where we've enhanced some of the services. So I realized as I was putting these slides together a few things. One, this is usually presentations that are given by 4 different people in about 15-minute increments. I think I can go a little faster than that, but the other is that probably 3/4 of what I present is setting the table for the Rapide testbed, which is the actual NSF project that has been funded. So thanks for bearing with me. I think there's some very interesting things here in setting the table. Let me quickly introduce myself. I am at Indiana University. I have been the ECSS L3 Manager of Science Gateways for about 6 months, maybe a little bit longer than that now. I'm also the Associate Director of the Science Gateways Research Center. I'm the PI for this enhanced robust persistent identification of data and its predecessor, which just left off the enhanced. And then I'm also the co-chair of the Research Data Alliance's Data Fabric Interest Group, which is really where a lot of this work was started, and a lot of the ideas were compiled to that led to an actual implementation and testbed of the digital object architecture. Unfortunately, digital object architecture has the worst acronym ever. So I will try not to say DOA too often, but if I do slip into it, that is digital object architecture and not what is more commonly referred to as DOA. So what I'll do today is basically answer some questions. One, why do we need interoperable data? And it may seem obvious to workflow developers such as the people on the call, but we'll also look at the social hurdles to interoperability and interoperability of data, which may be interesting. Where do we stand today? And that'll be a brief look at the history of infrastructure and the trends that are fueling FAIR principles. And FAIR principles, I know, is probably the most common overused acronym today, but that's data that is FAIR, which is findable, accessible, interoperable, and reusable. We'll talk about what the digital object architecture actually consists of, along with some of the background of building a infrastructure such as this, and what has happened in previous cases of similar technologies that were developed. And then we'll look at how we realize this architecture, and that's where the Rapide project actually comes in, is setting up an implementation of services that build this architecture. So we'll start with the UN Global Goals for Sustainable Development. And I think everybody can agree that the grand challenges require some data-driven solutions. If you go around each of these items on the UN's goals for sustainable development, you'll see where data can potentially affect them. And to deliver knowledge at a scale, form, and precision required to address these grand challenges and those associated with the Anthropocene, it's imperative we see scientific practice in the data it produces and the impact it has as a continuum. So basically as a supply-demand chain that is continually updated and analyzed. So I'll start with a quote from Christine Bergman at the RDA in 2014, which was coincidentally the first RDA meeting I attended. And he paraphrased Samuel Taylor Coolidge in saying, data, data everywhere, nor any a drop to drink. Now, I would say that there's plenty of data, and with the right right preparation, it can be. There's plenty to drink, much as water with the right preparation can be easy enough to drink. And I do want to. Well, we'll go back to it. So. Just a scientific publication. I think everybody's seen this slide or slides like this. There's this ever-increasing rate of global scientific production. Publications over time have more than doubled in the last 30 years between 1980 and 2012. And the question we have to ask ourselves is, will the open science, open data movement increase this rate even more in the coming years? And particularly in the interdisciplinary research and publications. And you can see here the impact of interdisciplinary research is still not at the level of interspeciality, but I think this has potential. The dotted line, the interdisciplinary publications have a chance to skyrocket, especially if we can get data in a homogeneous enough form to really use it in an interdisciplinary way. So pointing back to the UN's goals for sustainability, our challenges are global. We need global standards, global workflows, global cooperation amongst researchers. However, science is mostly carried out locally by scientists as part of a local infrastructure or institutional infrastructure. If you've ever tried to work on international projects, one of the biggest problem is that they have local funding. So it's very hard to get funding for a project to have more than one government pay for it, or for the funding to cross borders. We of course need to build some trust in the data that we're using for these grand challenges, and this includes trust in the practices in which the data was collected and stored, trust of the people who have collected that data, and then of course if you have the context and the practices and the people, then you can build data trust. And trust is lost when data sets get connected from that context in which they were created, or in the communities that created them. So again, everybody's probably heard that data is the new oil. I would say that data is not necessarily the new oil, just the well. And this means that trustful, fit for purpose information builds trust and reliable infrastructures, which is what we hope to at least have a proof of concept in E-RPID can change the modus operandi for doing science. So where are we today, and kind of more importantly, how did we get here? I will make the claim that data can be made considerably more useful with the right research and use case development, and the application pool exists for the usage of interoperable data, and that's basically the Internet of Things is around the corner, if not here already. Deep learning is dependent on increasing amounts of data, and the call for open science is being heard everywhere. I'll go into a few more of the details of that call for open science here in just a moment. And we know from several sources that in the several stages of data analysis, that data gathering and preparation, the exploration stage, before you can actually represent the data, transform the data, compute on it, make models and visualizations, is really consuming the vast majority of the time it takes a researcher to do an analysis. And at least in David Donahoe's books, The 50 Years of Data Science, it said that about 80% of this time is actually of a researcher's time is actually spent in that data gathering and preparation stages. And one of the things the digital object architecture attempts to do is really work with that 80% and see what can be done in the very first stages of data collection and preparation to reduce the amount of time. So open science is, as I said, the call is being heard everywhere. You can go back to the printing press, which enabled the explosion in scientists publishing their work. I guess maybe not the explosion in scientists, but at least of the publications that were then shared. Networked computers today enable the publishing of all science products. And the National Academy of Science, in a recent report, said that that was titled Open by Design, concluded that all research products should be made available according to FAIR principles. And this was also, actually, I should mention, echoed by a high-level expert group, including Baron Mons at the European Open Science Cloud, and it was recommended by them at the same time that all the data that is part of European collaborations with data in the Open Science Cloud in Europe be made available with these FAIR principles. So a few things have happened within the recent or past 10 years ago with data in US and US funding. First of all, in 2011, there was a senior steering group on big data, and it acknowledged that we can now store more data than we could effectively process. So basically, there's more data than we could ever actually act upon. In 2013, the US Presidential Science Advisor stated that all research products produced under research support should be open for public access. I think people who are familiar with grants are seeing this more and more. And then in 2014, in January, there was a workshop that where the FAIR acronym was adopted. FAIR, once again, just for completeness, is the findable, accessible, interoperable, and reusability of data products. So this was not only a policy change, there was also the hardware change that allowed this to happen with the incredible increase in the amount of transistors per chip, the increases in the networking capacity from megabits to experimental petabits per second speeds. Disk prices have dropped incredibly, and you can see the numbers here. I won't go into those. And basically, this great increase in performance and a decrease in costs has led to things that have enabled data-intensive science, machine learning, and other data-intensive use cases. So machine learning, people are, I think, at least familiar with the basics of this, really seen in two ways. Supervised learning, where you point the algorithm at a available data set to train a deep learning algorithm, so it can be categorized or used for direct actions. Unsupervised, which simply dives into existing data in an exploratory mode. In both cases, understanding the data is a requirement, and in fact, utilizing FAIR digital objects is really one way you can meet those requirements. So. In the era of interoperable computing, the creation of interoperable elements by introducing new levels of abstraction has always been a powerful science technique, basically abstracting various different levels, high-level languages, and their interpreters solve the interoperability problem for heterogeneous computing, basically language being used on computers that are not necessarily the same operating system or the same environment. The internet really solves the problem for interoperability on heterogeneous networks. And the digital object architecture is an attempt to solve this interoperability problem for heterogeneous data. So in a very fanciful way, and this is with some work done by George Strawn at the National Academies, you can kind of draw a picture to what may be seen in the future as the eras of IT. And again, this is kind of a fanciful look at things. In the first era, which was from the inception of computing to about 1995, you basically had many computers and many data sets all being separate, not being able to interact with each other. In that second era, from 1995 to what will be at least a few more years, there's been one of a single computer and many data sets. If you remember the Sun marketing slogan, the network is my computer, basically, for the most part, where the computing actually happens is transparent to the user. And in fact, the user doesn't care necessarily where the computing will happen. And then the question is, can we get to this third era, one where it will be a single computer and a single data set, that is the desired state of interoperability of all heterogeneous data. So at some level can, much like the network sees all devices exactly the same, can clients and applications see all data, at least at a very high level, exactly the same. So to get there, we'll need the digital object architecture. And one option is a digital object architecture. I won't even say at this point that the digital object architecture is going to be the winning, though I will say that I expect that this heterogeneous data problem to be tackled by one of many technologies which are attempting to get there at the moment. So basically, what infrastructure would be necessary to move to that heterogeneous interoperability of all data? Much as I said, as devices are completely heterogeneous, though they look exactly the same to the network. To go back, we should define infrastructure as a technology whose primary purpose is to enable or improve the use of other technologies. And this is not only a computing thing. You can think of the way the highway infrastructure improved the technology of the automobile, how air traffic control has improved the actual technology of airplanes. Same for electric grids and the internet for computer. And all of these technologies, and there are others, the telegraph, the railroad, telephone, electricity, as I mentioned, all have kind of this pattern of infrastructure development where there's a vision, someone comes up with an idea of how to do things, a creolization where several options are proposed, several technologies are active, though none fully adopted. Then some event leads to an attraction of that vision, and one or more of the technologies or some combination of the technologies in the creolization stage bubbles to the top, you get convergence and then exploration. So the historical pattern of what happened to the internet is you had this vision of one terminal connecting to any computer. You had then some wild west of the internet where you had vendor-specific nets. You had ARPANET, the OSI model came up during that time. It was eventually attracted, and the attractors were things like TCP/IP and packet switching and advances within the network. It converged around the NSF net and was eventually exploited with the technologies that we use routinely today, with things such as email, remote login, and file transfer. The hourglass model of the internet, here you can see at the bottom is the actual physical infrastructure, the copper fiber radio. On top of that, some abstractions up through the internet protocol suite, and then at the top, the exploitation, basically things like email, the World Wide Web, phones. Interestingly enough, while the internet, or at least communication, started off as a application of the phone infrastructure, so the copper wiring that ran to the phone, we've kind of turned that page now, whereas voice communication is now an application of the underlying fiber and internet. So it's an interesting progression there, whereas internet was or at least communication was computer communication was a function of the underlying phone infrastructure. Now the phone is actually a application on top of what is the internet infrastructure. So one more historical pattern here: the vision for the World Wide Web, easy access to information on the internet. You had some creolization with things like Gopher, www, and some other technologies. They were attracted by a protocol, again, HTTP. You saw convergent with various different browsers, and then the exploitation by all of the big names that we know today, such as Google and Amazon and such. So what we're looking at with data is there a historical pattern that's leading us to the next stage? So the vision, as I mentioned in the previous section, interoperable heterogeneous big data, that creolization where there's many technologies that are looking to be exploited. You have things such as MapReduce, the cloud computing infrastructures. The attraction, at least from what we see, is the fair data principles, which I think are pretty global, and then permanent identifiers or persistent identifiers, or PIDs, which the most commonly known one are DOIs that are attached to publications. And I think anybody who's published has probably seen a DOI, but DOI is just one form of a persistent identifier or permanent identifier. And the question is, what does this convergence and exploitation look like? We have this aspiration with the digital object architecture and with the E-RPID testbed that the convergence is around this global, open, fair, and digital objects, which I'll talk a little bit more about. And this can be exploited with the automation of those data wrangling steps, the steps that I said take some researchers 80, if not more, % of their time. And then open science is another exploitation of this truly open science. If you look at the hourglass model like we did for the internet, you see that we have basically at the bottom the local storage, which are at some level just bits on a disk somewhere, this being arranged into some relational databases and data sets, some data just held in files as digital objects, the PID being the center of the hourglass or the persistent identifier, with a resolution system typing. And really there's the services that we're building in Rapide and in E-RPID revolve around the center part of there, the digital objects, the PID, the resolution system, and the typing. So to attach this kind of to a object-oriented view, originally programmers built their own complex data structures out of arrays and recordings provided by programming languages. Next, abstracted data types emerged, hiding the data structure details and accessing the data structure only by defined operations, basically object-oriented programming. Now digital objects have been defined as self-identifying, so programs can query an object to find out what it is, and more importantly, which operations can be applied to the digital object. And we'll talk a little bit more about exactly what a digital object is here in a moment. The digital object architecture centers on these PIDs that point to digital objects. Digital objects really can be anything at any granularity that is necessary for the research. In fact, we've had this granularity problem a long time, is how how granular do you make your PIDs, and the result has been, as granular as you need them to do the work and do the high-level sorting and interactions that you need. A digital object interface protocol basically plays the same role for DOs. Digital objects as HTTP would play for web pages, facilitating other operations. If you think of the get, put, and various HPP protocol operations that all HTTP works off of, basically the DOIP is something similar with, in fact, some very similar operations such as get, delete, and there are other ones, I think, something that lists the operations that you can actually do. DOs can contain other DOs, so the outermost DO being a repository. DOs can also describe not just what we would think of as data, but of software, instrumentation. A DO can basically be applied to anything, much like a Unix system sees everything as a file. The DOIP would see everything it interacted with as a digital object, though you couldn't necessarily do all operations on all objects. And DOs contain not only data, but software, as I was saying, and most importantly, probably metadata. So I talked about FAIR a few times, but here's, in fact, I won't go into this detail right now. I see I'm already almost 30 minutes in. So, but this basically talks a little bit about the FAIR and why we consider it an attractor. So this is a high-level view of the digital object infrastructure where you have the end users with some sort of client or interface that allows them to deal with persistently identified virtually aggregated digital objects. And those objects include collection. Behind that, there is a set of services of repos, registries, and identifiers, which in the end overlay on some existing storage system. So basically, no matter which repository or storage system is on the blue end, you could potentially write a client to interact with it on a very similar way at the front side from the user end. And of course, the DOIP would send operations, which would be translated and do actual operations at the storage system. So some motivation here: if the digital object architecture coalesces the way the internet or the web did, the data infrastructure could be revolutionary. The Internet of Things will require a better data infrastructure than we have today to reach its potential value. Even where data remains in silos, a global fair data infrastructure can really increase. It could really automate and decrease the time it takes for data wrangling. And there's also the potential to facilitate a emergence of a data market. And this one's a little more provocative, but many people say that the open science revolution will be as revolutionary as the 17th century science revolution. So the ability to basically have everybody interact with this data could be revolutionary on a scale that we have not seen since the printing press and the publication of articles. So that was the table setting portion of the talk, and we'll go a little bit into how we are going about attempting to realize this. And please keep in mind two things. One, we're in the very early stages of this, of actually putting the services together that would allow the digital object architecture to be realized within a research environment. The ideas behind the digital object architecture actually stem back to the 1990s, so they've been around for a while. There's really not been the motivation with the things that I mentioned earlier, the hardware changes and the decrease in price, the Internet of Things and the collection of data on such a massive scale. And in fact, the DOA is really the brainchild of Bob Kahn. Bob Kahn is the co-creator of the TCP/IP protocol. When he really looked at the direction that data was going in the mid-90s, he thought that the device-centric internet would not propel us into the future, that we really needed a data-centric way to interact with data versus interacting with devices, which is what TCP/IP leads to. So, though really the momentum hasn't really started until recent times with the amount of data that's been available and the pushes into open science and open data. So the E-RPID vision starts with a data network based in the digital object architecture, a distributed architecture for services spread worldwide that will together identify and resolve the digital objects. The DOA, I mentioned Bob Kahn, so I won't talk about that again. It's basically a network of handle servers. And handle servers, again, a technology that's been around for quite some time. It's the technology that's at the core of the DOI system, which again has been around for quite some time. So the technology has been available. There's been recent updates to really enable this digital object interface protocol, which we are now looking at in Rapide. DOIs have a limited amount of usage for publications, though they're getting more and more into data sets. They usually publish on data sets at the publication point, not through the life cycle of data, where identification and persistent identification can actually be useful, at least in the opinion of many people, throughout the life cycle. So you don't necessarily need to wait till publication to give something a persistent identifier. And in fact, you can keep some provenance information by using multiple PIDs throughout the life cycle to identify, say, raw data, the software that's used to transform that, the processes within there, the instrumentation that may be added to it, and various different intermediate stages of data could be useful upon for the data lifecycle to show for reproducibility and reuse what was done from the raw stages to the publication stages, where things now first get a PID. So the other, actually, I forgot one thing when I was back on the previous slide, and I said to realize that this is in the early stages. Also realize that E-RPID is a test bed. So at this point, there are not production level services that are running, though the services are very reliable. They still issue test PIDs, which are not basically for use for test bed use cases, not for real life use cases. So if somebody thinks here that they would like to jump in Rapide and start issuing a lot of PIDs that they could then use for the future, that will not be the case, at least with the Rapide project. Now, if we have enough input that says people need live services and not just a test bed, then we can work on proposing something along those lines. But I do want to make sure that people know that Rapide right now is a test bed. So the required components to realize the digital object architecture are set forth here. There are really 6 things. The identifier, which is a globally persistent unique identifier, which identifies the object, has some, it also includes some data about the object, but doesn't necessarily include the object itself. It's the identifier, and one of the things the identifier usually resolves to is the location of the data. The identifier resolution, which basically gives some state information, some set of basic information about the data. A data typing service, which basically tells you if you're getting this type data, what that means. You can think of you're getting a collection date of the information. What format will that be? And that's for programmatic interfaces to interact with data. You find what the data type of each of the items in the state information are, so you can then further use that, especially in programmatic interfaces. A brokering and mapping service, this sits by the repo to prevent refactoring of existing repositories. Basically, we realize that if there's not an abstraction or a layer of an overlay to the existing repositories that were probably dead in the water, we can't ask people to refactor their repository to play in the world of the digital object architecture. The repositories themselves, which exist, and there are many types of these with many different interfaces. There are relational databases. There are just file systems that have data on them. There are specialized data repository services with well-defined APIs, et cetera. And then an operational protocol, which is really the center of this, which allows you to do basic operations with the data. Again, much like TC or HTTP has the get, the head, the post, the put, things like that. And in fact, TCP has some other limited set of options like listen and close and established and such. These basically are operations that allow interactions with digital objects, whatever those digital objects may be defined as. So in the Rapide testbed, we did, in the Rapide testbed was a NSF grant. I put the number here for anyone who wants to look that up. That ran from February of 2017 to February of 2019. That just ended. In fact, I'm writing the final report for that. That did the basic services, the basic core services, which are a handle system, which provides the identifier and identifier resolution, a data type registry, which does the data typing. And again, the repositories exist separately from the DOA. The repositories are usually owned by and administered by the group that's collecting the data. We looked at 4 use cases during the Rapide testbed. One was seed train, which collects environmental data, so basically airbox sensors. Some rice genomic data from Pragma. The Pacific Rim project is collecting various rice genomic data. The Perseus Digital Library, which is classical texts out of Tufts University. And then we looked at Jetstream VM images. And these basically, the set of images and whether putting them in a recognized identifiable format with a data type would be useful and interesting at some level. Let's see, and in fact, I can say that with the environmental sensor data and the rice genomics data, we found very good uses. The Persistent Digital Library, we published a solution as to how to move text-based information into a digital object architecture environment, though we didn't complete an actual implementation, mostly because the person who was leading that took on another position outside of academia where she was unable to continue there. And then the Jetstream VM images, we went back and forth. Jetstream VM images already have DOIs assigned to them, and there's a limited enough number that at least when we attempted this in 2017 that a large value was not seen, basically because there were only 70 some images at that time, and they were easily sorted and acted upon outside of having another overlay of abstraction with the DOA. So I am going to move forward here a little bit, and something to keep in mind here, digital object architecture is a base infrastructure only. It doesn't say anything about content, relationship to metadata, relationship between data. To that, we turn to FAIR principles. And in fact, some principles put forward by the PID kernel information working group. There are some additional slides at the end that I won't go over that talk about what the PID kernel information group is. They basically recommended about 17 pieces of metadata that could be stored within the handle system that would allow you to build some initial trust. So if you imagine the internet scale data client is handed a list of 100 million PIDs, how does it quickly shift through the list and find data objects, and further suppose the client is able to winnow that list down to just research data objects, how do they quickly discard the fakes? And that's one of the questions, the real high level sorting that we have delved into, especially with the airbox data. And how it would do it is something along this line. The client would talk to a global handle registry, which would point it at a local handle registry. You can see this looks very much like the DNS type services now, where a global registry points to a local registry. That would get then the handle information, which is some state data. Here, it would then check the DTR profile, the data type registry, to be sure that it could understand the data and had definitions of the data types, which then it could do some filtering and decide which ones are trusted data objects and which ones need to be filtered out. So some outcomes with Rapide. We basically had specialized clients working with the Rapide services, and they could do this high-level sorting. So you could, for the airbox data, put in a date range and only get back the data objects that you were interested in that single data source. Now, that doesn't do a whole lot for interoperation. The interoperation is really more in the area of E-RPID, which I will get to here in a second. For the sake of time, I will move forward. E-RPID, we added the mapping brokering services, and in fact, this is work that is ongoing today, and I've invited Marina Krentz, who is working on this. Unfortunately, the PhD student who is also working on this and doing the majority of the effort in this was unavailable today. He's actually, I think, going to Korea to participate in the Pragma event, which is where we get the rice genomics data. So he's interacting with the use cases on a face-to-face level. And then really taking a look at this DOIP, the operational protocol, and seeing if we can enable the basic operations to interact with data repositories. We've added a few additional use cases, one being the Science Gateways Research Center is going to look at what this looks like as the back end for data management in things like SeaGrid and other gateways. And then Galaxy has also agreed that we could take a look at their common workflows and see if we can find some advantage in moving towards a digital object architecture. And then we'll continue on with the seed train data and the Pragma Rice Genomics data use cases. Again, now they shouldn't have to have specialized clients like we built in the Rapide grant during the E-RPID. E-RPID started in October of last year. It goes on for 2 years. It's an eager reward. If people are not familiar with the eager mechanism, it's for the high risk, high reward type grants. And we hope to, by the end of this, have at least some push into non-test bed status for this type of services. So again, this just separates what is on the client end from what was Rapide. Rapide being the handle service, basically the issuing of PIDs and resolution, the data typing service, then adding a mapping service. And if I were to redraw this again today, I would put the mapping service next to the repository. And then the digital object interface, which actually allows, again, a certain set of set operations to interact with the digital objects themselves. There are a variety of E-RPID work items, which I won't go into. And what does this look like? We gave this to you, the grad student, and Marina to kind of write up what a workflow would look like. It looks like this. I don't expect everybody to look at all this, but basically you have some basic operations. You have a user who makes a request based on either some sort of query or a set of persistent identifiers. It interacts with a mapping engine, which maps the repository, talks to the handle system in the data type registry service, and either returns or performs the operation requested by the users. This is still in an early stage of drawing up. And I will say a few more things and then wrap it up. And it looks like I'm right at the 45 minutes. So, some conclusions: IT is poised to do for data what the internet did for networks. E-RPID and other DOA type services could be the start. I'm not saying they will be the winner. There's a lot of push behind them, but there are other people playing in the same area. Interoperable data will become a core infrastructure, much like the internet has already become, and in some number of years we'll wonder how we ever got along without interoperable data. And to keep in mind, science is really a lights better endeavor. Research effort is not directed to the areas where the work is technically infeasible. It's directed where real interpretable results may be obtained. We do in fact conduct research where light's better, but when the light changes, so does the science. So illuminating more of the data potentially leads to better illumination in all areas of science. So I think I will wrap up. There are some additional slides, and I'll get these slides out to Bob and Marcus to post the additional slides. Just talk a little bit about the PID kernel information, which you can see here, and a few other things. And with that, I know I set the table for a long time. I introduced E-RPID. I didn't talk a lot about the technical details. For the technical details, as people are interested, we can talk about the various ways to interact with the API and other things. But in the end, I think the takeaway is interoperable data is inevitable. And what infrastructure do we really need to get there? Again, I'm not sure what the winning technology will be. I'm rooting for DOA, and I think it has a large start, but I think interoperable data is inevitable, and we'll see how we get there. So thank you, and I'll, I guess, take some questions.
Thank you, Rob. If you have any questions you would like to ask, feel free to unmute your mic. Oh, there is one from Marlon. Can you show the PID kernel info slides?
Sure. Are you still seeing this, or did I?
Yep, we can see your screen.
Okay. So let me go back to putting this full screen here. Can you see it there?
Yep.
So this is the kernel information. It's basically what the working group within RDA put forth as generically what should be attached to every piece of data. You can see there are some mandatory and some non-mandatory things. These have things like you can see number 2 here is the profile type. That basically is what the DTR, the data type registry, so it knows how to match a profile with the actual data. The digital object type is I guess the object location here is important because that's where the actual object is located. It's not necessarily a URL. Things that establish trust and provenance, like an E tag, possibly a checksum or some other identifier. And then as you get further on here, version and such, these are more provenance related items. Again, you can see that none of them are mandatory, but they can potentially provide a string of provenance of information that basically you can see what the history of the data is gone through. And I'm not seeing the chat window, so if anybody, Marcus, I'll let you read what pops up there.
Yeah, that was the only one that was in there. Yeah, feel free to ask any questions. Otherwise, in a moment, we'll do a last call.
I do have some questions. Thank you for that very interesting talk, Rob. I was wondering, this DOA architecture, are there mechanisms in there for sort of access control and ensuring the integrity of the information? I know you mentioned sort of at a high level these are issues, but I was wondering if there are
Yeah, at some level, access control is something that's set forth by the repository. And of course, interacting with that access control is going to have to be taken into account. And basically, when some operations will be feasible while others not. You may have access to a repository to read the information, but not delete or write the information. You can see that we have an authorization, and I don't know if you can see my cursor or not, but on the kind of right-hand side here, there's a setting up an authorization. But access control, again, much like the web page server determines who access and where access control is. Now we'll have to carry some authorization information forward to determine access control. But at some level, that's the repositories. The repository already has an access control scheme, right? And we're going to have to interact with that through the mapping engine.
Okay, thank you.
So yes, that is a important thing, and I think actually one of the more difficult things that we'll have to solve is how to really make sure that the end request is that basically access control and authorization is enforced throughout the process. One of the tougher nuts to crack.
All right, any more questions?
Hi, Rob. This is Junan.
Go ahead.
Yeah. Exactly, what do you mean by data interoperability, something like, okay, for example, I have like a global, data object and like I-RPID, data object. This is like, how does exist in a mechanism, interoperability between them, something like that.
So in the end, I guess who this is for is not necessarily for the end users. It's for the person who is writing the clients that are, or interfaces that are interacting with this. And where the real advantage is that those who are developing an interaction with a repository can develop the same way for repository X, Y, and Z. Now, how it interacts with specifically Globus and I-RPID's technology, there'll have to be some sort of mapping going on there, but I'm not familiar with either of them, the technical details of either of them well enough to say exactly how that's happening. But in the end, what the advantage here is that the much like developing on a developing a mobile app, you are interacting with a network. It doesn't matter that the app is necessarily mobile, at least not to the network, right? So here the idea is it doesn't matter what the repository looks like or the end where the data is stored looks like, you interact with it in the same way.
Yeah, I think there are so many different type of metadata for based on science domain. So I know a lot of like I forgot that one, but there are geoscience metadata format, something like that. So I'm just pretty much interested how RDA make like interoperable between those data objects.
And keep in mind, so two things. One, this doesn't replace a metadata server, right? You're still going to have metadata published. And in fact, only a small amount of metadata can be held in the resolution system, so within the handle system. This is because really this has to scale to internet type speeds. You don't, and if you end up putting trying to put all of your metadata here in the kernel of the request, then you're basically going to clog up and not be able to interact quickly and do the high level sorting. So one, this does not replace having some sort of metadata repository or published somewhere to get more details. But for quick, high-level interactions with data, again, in any repository, you should be able to do that in a consistent manner.
Yeah, in the last week SGCI webinar, Data One also integrating a lot of different type of repository, but they just provide a federate search engine, something like that.
Mm-hmm.
Yeah.
And usually a federated search engine does covers the findability and sometimes the accessibility, but really doesn't necessarily mean. It just means you can find the data in a consistent manner. It doesn't necessarily mean you can interact with the data or do operations on the data in a consistent manner. So really, it focuses on the F in FAIR, not necessarily interoperability. You still have to, if you find things that, even if you do a search and find things in different repositories, you still have to do a lot of that data wrangling to be able to actually have it in a interoperable state.
Okay. Thanks, Rob.
All right, well, thank you everyone for joining us today. As always, this symposium will be posted on the Ecss website. And thank you, Rob, for presenting today.
You're welcome.
Thanks, Rob.
You're welcome.